Hi there, Andy Warwick here with the second video on the cultural history of theoretical physics. In this one I'm going to be talking about my work on mathematical physics in Victorian Cambridge. In the previous video I showed a slide of Einstein's early work as the history of ideas, and for mathematical physics in Victorian Cambridge an equivalent slide might look something like this. In the 1980s, historians of mathematical physics were supposed to show who'd got to which equation first and how they'd done it. The how was in published papers like this one. This is J.H. Poynting deriving his famous energy flow theorem, now known as the Poynting vector, in the Philosophical Transactions of the Royal Society in 1884. He derived the vector from equations given in James Clerk Maxwell's famous treatise on electricity and magnetism of 1873, in which Maxwell gave the first mathematical field theory. As you probably know, the Poynting vector tells you how energy moves in an electromagnetic field. In this classic image, Poynting is a latter middle-aged professor, and his proof is a standard textbook derivation. That's what mathematical physicists were supposed to do. Building on work in the sociology of scientific knowledge, I began trying to develop a new approach, which, as I said at the time, put some inertia back in the massless particles of ideas. Instead of taking technical expertise for granted, I wanted to make it the problematic. What historical processes made men like Poynting? What could they do? How did they do it? How did it shape the theories they went on to make? How did their theories move over historical time and space? That project ultimately took me something like 18 years and was published in 2003 by Chicago University Press as Masters of Theory. That's me around the time I began this project, and over those 18 years it grew into something much bigger. When Isaac Newton published the Principia in 1687, only a handful of men had the technical expertise necessary to read it. Much the same was true over the 18th century as rational mechanics and then physics was born. But from around 1800, new regimes of training began, first in Paris and Cambridge, which multiplied those technical skills, eventually going global. Using Cambridge as my example, I wanted to describe that process and find an answer to my question. If physics was a culture of its own, what kind of culture was it? Now, I know reading a nearly 600-page book is very last century, even for historians, so I have remade the book as a one-page graphic novel. I began with an epigraphic verse by James Clerk Maxwell, you can see it on the top right, one of the two most brilliant mathematical physicists Cambridge produced in the 19th century. He's bemoaning the drudgery of undergraduate studies 6 months before he had a serious breakdown due to overwork. I wanted to flag an approach where the body of knowledge refers to the knower rather than the known, where knowledge is always the possession of initiated subjects. We just saw the middle-aged Poynting with his logical derivation of the eponymous vector. In the centre of this graphic you can see an exam script the 24-year-old Poynting wrote in Cambridge's Senate House in 1876. His name's on the top right. And you can see the difference. He's working in real time against the clock, changing his mind, crossing things out, negotiating with himself, so to say. There's no logical certainty, no neat derivation. It's a young physicist on trial, still learning his craft. Around the paper are the resources that made Poynting what he was. At the top, his mathematics coach, Edward Routh. The quotation is from his coaching notes. To Routh's left are books of past exam papers, exemplars as Thomas Kuhn called them, models of what a research problem is and how it's correctly solved. Below that, class teaching on a blackboard. Bottom left, competitive examinations written in policed silence. This was a huge change from the public disputation in Latin that had dominated undergraduate examination for more than 500 years, a change demanded by technical studies. Right of the exam is team sport as a model of manly competition, the co-shaping of mind and body. Competitive sport was established in Cambridge alongside competitive examination. The term coach was first a math tutor, then moved to rowing, and then beyond. The exam results were published in the national press as an incitement to heroism or fear of humiliation. You can see a list on the top left. The first-class men were called wranglers, the top man the senior wrangler. Women were excluded because it was said they were unsuited mentally to a system that routinely pushed men to mental breakdown. Until 1890, when Philippa Fawcett, champion hockey player, informally beat the highest scoring man. The book draws an organic portrait of undergraduate study by drawing together the history of mathematics, of institutions, of sport, of science, of the body, of education and examination. Mathematics is depicted as a set of embodied skills, not just a language of physical theory, but an instrument of the state, of masculinity, of competition and ranking, of elitism and social mobility. The Cambridge Mathematical Tripos, remember, wasn't primarily to train mathematicians, but to rank the British ruling classes. So that's my sketch, my macro scheme of the Cambridge experience. But I wanted to include research as a natural strand of that world. And to illustrate this, I'll return as an example to Poynting's work in electromagnetism. Okay, so here we are again with the carefully constructed portrait and proof. I chose the Poynting vector or energy flow theorem as one of several case studies in the book because this piece of late Victorian physics seemed at first sight to refute the idea that research was always bound to highly trained, closely connected communities. But Poynting was in Birmingham when he wrote the paper. There was no research community there. His research to date had been entirely experimental, measuring the gravitational constant G. He wasn't taught Maxwell's theory as an undergraduate and had in fact shown no interest in this kind of theoretical research to date. Did he just pick up Maxwell's treatise, turn to the notoriously difficult general equations and deduce the Poynting vector from first principles? If he did, I'd go back to doing the history of ideas. So let's transform Poynting and see what I found. Born in 1852, Poynting initially studied physical science at Owens College, Manchester, before going to Cambridge, where he was third wrangler in 1876. He went back to Manchester as a physics demonstrator, where he built an apparatus to measure the mean density of the Earth. This work won him a fellowship at Trinity College, Cambridge in 1878 to work at the new Cavendish laboratory with Maxwell, again measuring the mean density of the Earth. In 1880, he took up a new physics professorship at Mason College, Birmingham. Poynting took teaching very seriously, sometimes publishing his pedagogical innovations. One such in November 1883 concerned a simple method for deriving the velocity of sound by considering how longitudinal waves transmit energy in a medium. Bottom left, you can see the paper and Poynting's laboratory, his teaching laboratory in Birmingham. The trick was this can be done in two ways. First, by assuming the total energy in a given volume behind the wavefront moves with the wave into an equivalent volume in a given time. Second, by assuming the energy delivered to the medium by the wave can be expressed as the work done by the advancing wavefront. A combination of these results showed the velocity of the wave is the square root of the elasticity over the density of the medium. Poynting then showed the same trick worked for transverse waves and applied it to several mechanical cases. In a footnote, he revealed the technique was, quote, merely an application of a wider analysis given at the end of Volume 2 of Lord Rayleigh's treatise, The Theory of Sound. You can see that bottom right. In a subsequent letter to Rayleigh, the senior wrangler of 1865, Poynting revealed this was also the starting point for his research in electromagnetic theory. And I quote, I tried to get a simple proof for the velocity of sound and of transverse vibrations, and an attempt to apply the method to Maxwell led to the law for the transfer of electromagnetic energy. But how? In seeking equivalent electromagnetic expressions to the mechanical ones he'd used so far, Poynting was plunged into the most difficult sections of Maxwell's treatise. Yet, just 5 weeks later, in the middle of a busy term, he sent the completed energy flow paper to the Philosophical Transactions. To see how he did it, we must go back to the tripos Poynting sat in 1876. One of his examiners was Lord Rayleigh, then writing his treatise, The Theory of Sound. Rayleigh used some of his current research to set problems for the most advanced candidates. This practice reveals a connection between research and examination peculiar to Victorian Cambridge. Examiners used the Senate House exam to claim priority for new results. The students were set problems they couldn't possibly have seen before. Top left, you can see one of Rayleigh's problems, asking the student to calculate the energy transmitted by an oscillator at the vertex of a cone. It's a surprising result because the oscillator transmits more energy in a narrow than a wide-angled cone. When Poynting went back to Cambridge in 1878, Rayleigh was just publishing the second volume of the Theory of Sound, and in it he gave the solution to the problem. You can see it there top left below the problem, and beneath that his reference telling you it was a tripos problem in 1876. The book was keenly studied by Poynting and his peers, partly because it was the most advanced treatise on vibrations, but also because it gave the solutions to the problems they'd struggled with in the tripos exam of 1876. That's how Poynting knew where to look in the treatise in 1883 when seeking a simple derivation for the velocity of sound. What's more, W.D. Niven put on the lecture course at Trinity College at this time to try to teach the general equations and the electromagnetic theory of light from Maxwell's treatise. Niven, who's top right here with Maxwell, was third wrangler in 1866, a tripos examiner, lecturer at Trinity College, friend of Maxwell's, and editor of the treatise' second edition. It was in this classroom that a generation of wranglers, J.J. Thomson, Joseph Larmor, Richard Glazebrook and so on, began formulating research problems that would bring Maxwell's electromagnetic theory to life. Poynting described Niven as, quote, so well acquainted with the methods of research, he was able to give sympathy and encouragement to those of his students who were strong enough to question nature for themselves. In 1883 then, Poynting was one of a very small group of mathematicians who had a real working knowledge of both Rayleigh's and Maxwell's treatise. I suggest that his route to the eponymous vector was something like the following. When he tried to apply his simple method to derive the velocity of light, he quickly got into serious difficulty. The first expression he needed wasn't hard to find. Maxwell's equations for the total energy in the field are top left, but he gave no equivalent for the mechanical work done by the electromagnetic forces advancing in the medium. What did Poynting do? We now move into the realm of informed conjecture. Remember Poynting's letter to Rayleigh that accompanied the draft paper. He'd read Rayleigh's work and was, quote, led to the law for the transfer of electromagnetic energy. My sense is that Poynting turned again to Rayleigh's theory of sound. In the very chapter where Rayleigh solved the 1876 tripos problem, he also showed how to split the total energy in a wave-carrying medium into various forms of surface and volume component, as you can see top right. Poynting, beginning with Maxwell's equations, did exactly the same, differentiating with respect to time, then using substitutions and integral theorems to split the energy into component form. He found the term he wanted, but thanks to his lectures with Niven, realised he'd found something much more important. In the early 1880s, Maxwell's general equations were little known and conceptually obscure. Maxwell worked with potentials, not forces, and as Poynting said, most electricians imagined an electric current as something travelling along a conductor, taking the energy with it. But as Niven had taught Poynting, according to Maxwell, energy had to be, quote, seated everywhere in the surrounding medium. It was hard to conceptualise this, let alone understand conduction. Poynting's integral form of the energy flow theorem shed remarkable new light on this process. As he showed in a series of examples, the energy stored in the field, quote, must flow along the electric and magnetic level surfaces. Here's a drawing of a battery discharging through a wire, showing the lines of electrostatic equipotential. If we add the lines of electric force and the magnetic field around the wire, and then add their cross product, the Poynting vector, we see the energy from the surrounding ether flowing into the wire. The field is replenished, Poynting said, by energy from the battery flowing along the equipotential lines. This was a major milestone in clarifying Maxwell's electromagnetic theory. The focus of attention is now on the dynamical state of the electromagnetic ether, the battery and wires reduced to mere sources and guides. As Poynting says at the bottom, we must understand the core in a submarine telegraph cable merely as a means of getting the energy in motion along the insulation. Poynting presented his paper as a problem, quote, we are naturally led to consider by Maxwell's theory. Yet its consideration wasn't natural. None of the professed experts on Maxwell's theory, including Maxwell himself, had found it. Poynting's route was unique, but deeply entangled in the culture of the mathematical tripos. That's why it was natural for him to present his results like a tripos problem, a theorem followed by its applications, the calculation of the velocity of light, now reduced to a mere corollary at the very end. I've presented this culture as local, but its boundaries are managed and porous, always sifting the possibilities of the wider present. To see this, let's follow the energy flow theorem beyond Cambridge from the local to the global. And here I'm going to be asking two important questions. First, was this the only way the Poynting vector could have been found? And second, if its origins were so local, why do we now regard it as globally valid? See you in the next video.